Good morning, everyone. Thank you for coming. Everything I talk about today will be joint work with my advisor, Matteo Viale. So, today, we will try to understand the relation between two objects. First, infinitary logics of the form L infinity omega, and second, Boolean valued models. Now, this is a very general project, and I personally believe that the best approach to understand something as general as this is to have a precise goal at the end, and the goal for us will be the following result. So suppose you have an infinitary sentence with something that we will call the ASK property. Well, in that situation, one can build a sequence of consistency properties and iteration such that forcing with the last one is stationary self-preserving and builds a model of the sentence. Now, this statement probably doesn't make any sense for you right now, and that's completely normal because, well, I didn't say what this ASK property is. I didn't say what is a consistency property. Well, maybe you know, but probably you don't know how to force with it. And finally, I didn't discuss how to iterate this type of forcings. So I hope at the end of the lecture, all of this will be more clear. And our path to do so will be the following. So I start recalling a bit what infinitary logics are, and I will introduce the point that will guide our work, which is the failure of compactness and what can we do about it. To discuss compactness, we need a bit of Boolean valued models, so I will recall what they say. And once we are ready, we will introduce a version of compactness for infinitary logics, which we call conservative compactness. And these 4 items correspond more or less to what we could call the model theoretic part of this talk. Once we are equipped with all these techniques, we can go to set theory, introduce consistency properties, start forcing with them, and finally discuss how to iterate them. Okay? So everything here will be very guided with one intention, but this here below will be the first main point in the talk. Okay, so let's start. Infinitary logics, what are they? Well, I always like to warm up furthermore after dinner last night with a very simple example. So let's start with the graph given by the integers, normal graph. And now let's make 2 copies of the same graph. Well, the first graph is clearly connected. The second graph is not connected. One can check that they are both first order equivalent. And this shows that connectedness is not a first order property. It holds for one, it doesn't hold for the other, but they have the same theory. So no first order property. Very well. Nonetheless, if we fix the length of a path, then it is very simple to write a sentence in first order that says you have a path between 2 points in your graph. This is probably one of the first sentences we learn as logicians. And this tells us that we have a problem for which we don't have an axiom, but for all approximations, we have axioms. And this is the same very situation in which the great mathematician Carol Karp found herself in the 50s. So one day she was discussing with her advisor, Leon Henkin, and she told him, and this is from her book, that a problem would be very easy to solve if she could just consider a disjunction over the natural numbers. Okay? To which her advisor replied, "When do it, well do it." So this is what we are going to do. We have all approximations, but we don't have the limit. If we consider a disjunction over all the approximations, we obtain an axiom for being a connected graph in a very simple logic. Now, being a little bit more formal, what are infinitary logics that we will consider today? So they are given first by a regular cardinal kappa, and they generalize first-order logic with one new rule, which says instead of finite conjunctions and finite disjunctions, well, you can consider conjunctions and disjunctions of size less than the cardinal. Now, this is the set size version, and if one wishes to consider the class version, well, you only consider all regular cardinals, and you have the logic that allows to consider arbitrary conjunctions and arbitrary disjunctions, set size, but of arbitrary size. It will be very convenient to work with what we call the quantifier elimination for set theoretic purposes. And this axiom simply says that if you have a language with a set of constants, you can write an axiom saying every element in every model has to be the interpretation of some of these constants. Now, why is this convenient? Because now we can eliminate the existential quantifier as a disjunction over the set of constants. And we can also eliminate the universal quantifier as a conjunction. Okay? This is not extremely important, but it's very convenient for the proofs. So let's assume, I will try to recall it when I use it, but it will be more or less implicit in everything we do. Okay. Now, if we are honest, this logic seems very nice, but there has to be a reason for which most people here are not using them every day, no? And the reason is probably the failure of compactness. We like logics with compactness, and this fails very bad for this type of logics, okay? So let's analyze that. So we move to the second point, which is the failure of compactness for this type of logics. And let's do it in the most simple example, okay? So consider a language which has omega plus one many constants and a binary relation symbol. And consider the theory saying that the constant index by omega equals sum of the constants indexed by natural numbers. Then order the constants following the indices. And finally say that the constant index by omega is greater than all the others. But this is an infinitary theory because there is one infinite disjunction. And if we consider any finite subset of this, well, we have a model, okay? Because it is enough to interpret C omega by the biggest constant appearing in your finite subset. Well, you go above that, and you can produce a model. But there cannot be a model of the theory because the constant C omega cannot be itself a constant index by a natural number and above all natural numbers, okay? Okay, so this is usually considered enough to say, yes, they are implicit, yes, sorry. So the order has to be a linear order so that the order relation implies that you are not equal, but yes. This is usually considered enough to say compactness fails, let's try something else. But today I want to convince you that if we analyze this a bit more deeply, we can get a very nice result. So let's do it. I think we can all agree that the problematic axiom is this one. It is the only infinitary axiom we are considering in this theory. Otherwise, everything should be possible. What is the problem here? As soon as you fix any subsentence making true the axiom, okay, so you fix any natural number n and you make true the axiom by saying C omega equals Cn, as soon as you do that, you have a subsentence which is consistent with the original axiom, but is not consistent anymore with cofinally many of the other elements of the theory. Okay? Now, why do I say this? Because in first order logic, it doesn't matter how you realize finite subsets. You have compactness that says every finite subset has a model, well, then your theory has a model, but you don't care about how you realize those models. And here I'm pointing to a detail that says for infinitary logics, sub-sentences will be very important. So when you realize a sentence, you need to still being able to play the game with the sub-sentence realizing this. So this will be the key notion that will allow us to generalize compactness. Let's make a definition formalizing it. It says, you have two formulas, one stronger than the other, and we want to measure how far they are one from the other, okay? Because the problem with the example before is that the infinitary disjunction is very far from the other sentences in the theory. So we need to control that difference. And this is how we do it. You have two sentences, and one is possibly in a richer signature than the other. And you say that the strong sentence is a conservative strengthening of the weak sentence if whenever you realize the weak sentence with subformulas that are consistent with it, well, then the strong sentence has to be also consistent with that. This is the key argument in everything we will do today, okay? So, let me repeat. The problem is that we cannot just say this sentence is stronger and this is enough. We need to measure the difference between both sentences. And the difference will be measured by this conservative thing we add, which says you take sentences, sub-sentences of the weak formula. If they are consistent with the weak formula, then they have to be consistent with the strong formula. I will arrive to that. Now, as Joko very well pointed out, I have been talking about normal models up to now, but in order to formalize this better, we need this notion of Boolean consistency. So now we are going to introduce that, and then we will come back to finish this problem, okay? So, Boolean valued models. Let's start by recalling what they are and what they give us. Now, the main idea for Boolean valued models is that they generalize the truth value from Tarski semantics. So, Tarski semantics says something is either true or false. Well, with Solovey and Scott and the development of Boolean valued models, we took a more general approach, and now truth is an element in a Boolean algebra. Now, how do you define the truth for these Boolean valued models? Well, first, you have to define the structure by hand. So this is the same thing as in first order. You define the value for atomic predicates, and then you continue by induction using now the rules of the Boolean algebra. So you define by hand the function for atomic formulas. For negations, you realize that in a Boolean algebra, there is a very canonical definition of what is the negation of the value. And if your Boolean algebra is complete enough, then you realize that these are very well in connection with infinitary logics, because you can just define the value of an infinite disjunction as the soup of all the values. And the same thing for disjunction, for conjunction. Okay, now, Boolean valued models are a very nice idea, but again, they don't always work well. And one of the reasons is the following. So, what are good Boolean valued models? So, a Boolean valued model is said to have the mixing property. Whenever you consider an antichain in the Boolean algebra and you index names using the antichain, well, then you can mix all the elements in one single element in your Boolean valued model, and no matter how you realize truth, this element will equal the elements, okay? So this is very common in forcing. This is one of the first lemmas one proves using choice to start doing forcing. And why do I say that this is the right condition to deal with Boolean valued models? Well, there are two properties. The first, that when we have mixing models, we have this notion of fullness. So the problem is that when we realize a disjunction as a soup, there is no reason in principle. So here, there is no reason in principle for which any of these formulas has to take the same value as the soup. And actually, it doesn't happen usually. Well, we say that for mixing models, this actually does happen. So whenever you have an existential sentence, you can always find an element by mixing all the witnesses that will realize the formula with maximum value. Now, for a logician, if you have an existential sentence that is true and you can take a witness, well, that's somehow very convenient. And the second property is the following. And this goes a bit far from this talk, but there is an old theorem by Monroe that says, well, this has to be formalized properly, which I'm not going to do, but if you see Boolean valued models over a fixed Boolean algebra, well, one can see them as pressures on the category given by positive sets in the Boolean algebra. Okay? And recently, my advisor, Matteo, with another of his students, showed that mixing models correspond with the nice models in this category. So if general Boolean valued models are pressures, mixing models correspond with sheaves. And furthermore, the sheafification operation in this category is given by the Boolean ultrapower, which I have not defined either, but this is just to give you an idea that sheaves are about gluing things together. And it is very natural for me to see that actually this ultrapower, which glues together a lot of things, has a very natural correspondence. So, reason one for these models is fullness property. Reason two, this nice category theory result. Okay, so now we already know what Boolean valued models are, and we can come back to our goal, which was understanding this compactness problem. Let's go to what we call conservative compactness. Now, since this is very dependent on the definition I gave before, I'm going to repeat it because it is maybe not transparent at first sight. So recall you have two sentences, one is stronger than the other. They are not so far from each other, so one is a conservative strengthening of the other. If for consistent subformulas of the weak one, the strong one is consistent with them. And this is precisely what fails in the example I gave out compactness. As soon as you realize the disjunction, all the other sentences are not anymore compatible with it. Okay. Sorry? Yes. Yes. I will. Probability, yes. I mean, the natural sequent calculus for first order logic provides a completeness result for this type of Boolean valued models with the mixing property. Okay. So yes, Boolean consistent means you have a Boolean valued model, yes? Very good question. So what you should be thinking about is finite subsets. So the finite subset is the strong formula, and the elements inside the finite subset are the weak one. Okay, so compactness for first order logic says if every finite subset has a model, then the whole family has a model. While here, what has to be considered the strong formula is an arbitrary subset of this family. Okay? So you have an infinitary family of sentences, and you say that this family is finitely conservative, which means every finite conjunction you take in there is not very far from each of the elements, which is clearly not true in the example I gave, because in the example I gave, all the elements were atomic formulas, but one was an infinitary disjunction. And this is very far. So you get this notion of infinite family that is finitely conservative, and with this you can prove the theorem we wanted, which says if you have an infinitary theory and every finite subset is a conservative strengthening of the elements, so the family is finitely conservative, well, the conjunction is Boolean consistent. And furthermore, it is still a conservative strengthening of all the elements, okay? So even if you take the conjunction of a huge family, this is saying that this will not go very far from the elements. Now, you might be thinking, well, but you said that we were going to generalize compactness, but then you switched to Boolean valued models and you did it. You like Boolean valued models like I do, you should be happy. If not, when we come to forcing, we will see how to transform this into Tarski models, okay? I think this is the right way of seeing this result. Yes. Sorry? In L omega omega. No, it implies it for first order logic, but for infinitary sentences it's stronger. Yes. Yes. Yes, it is. Okay, so this is the main result for the model theory part of the talk. Now we can be moved to something a bit more set theoretic. So I said that this theorem is true, but I did not say anything about how you prove it. The reason for this is that we need the main tool for infinitary logics. So this is really the main way of building models in infinitary logics. So consistency properties. Now the way to understand what consistency properties are and where they come from is to analyze the proof of the main logic results for first order. You have compactness, you have omitting types, you have interpolation, you have completeness. Well, if you look at the first proof you are given in those theorems, you usually use compactness. Well, actually, no, because for the omitting types, you don't use compactness. For the omitting type, you use a diagonalization argument, which is more of a set theoretic nature, in my opinion. And this is what we are going to do. We are going to take the idea, well, this is what people in the 60s did, not what we are going to do, but let's recall it. So, what is a consistency property? Recall that we work with quantifier-free sentences. A consistency property for a logic, well, first you pick a set of constants that is fresh, so this will be the model later, but the point is that consistency properties are finite approximations for building a model, okay? If you want to think about this in a very forcing way, well, call omega omega 1 is made up of finite approximations to a cofinal sequence in omega 1. Well, consistency properties are giving you finite approximations, well, not always finite, but approximations for a model. The first thing you need to ask is that every element is consistent, well, because if not, you're lost. The second thing you need to do is to say, whenever one approximation realizes a conjunction, well, you need to be able to extend the condition with one of the elements, okay? Look that this is already looking very similar to this subsentences thing. When you realize something, you put the formula inside. when you take a disjunction, well, you need to choose one, okay? And then you have three conditions which are of a different nature. They are just intended to allow you to define what will be the ground model with an equivalence relation. But really, in my opinion, the important part is this, the logic connectives. Okay? If you look at the other three, well, it is very clear that they are intended to define an equivalence relation. The S in the first point. Well, okay, let me read what I wrote. Okay, so quantifier-free sentences such that for every element in S, so for every small s in big S, all of this happens. So I'm sorry. Okay, yes. No, that's okay. So a small s is an element, and big S is the set of approximations. You say, for every S in S, for every phi in S, all of that happens. Yes. Okay. Well, I'm very sorry. So why is this notion important? Well, when they realize compactness fails for these logics, they search for a new tool for building models. And this is what Mackay realized, that if you have a consistency property, then any element in the consistency property, so any approximation to a model, can be made an actual part of a model. Okay? Now, this works only for the first infinitary logics, L omega 1 omega. And you need consistency properties that are small. They have to be countable, and all the elements inside have to be countable, because you are going to diagonalize, and you are going to meet countably many dense sets. You can only do it in that case. Okay? Yes, this is what my advisor told me today, and I fixed it in another place, but not in this one. Here, consistent is Tarski consistent. Now, this is the theorem that started this field. And the corollary, which in my opinion is, I mean, the proof doesn't give any information, but I think it's even more important. It says, if you want to build a model, well, try like this because there is no other way. You have a sentence. If it has a Tarski model again, well, then there has to be a consistency property. One element in the consistency property contains your sentence. Okay? So this is what was done in the, I believe, in the 60s by Mackay, Kissler, Chang, and these people. And what we are going to do is to generalize this to the general case. Okay? Now, in order to do so, one needs to be able to force, because we cannot meet more than omega many dense sets. So we need to describe a method of forcing with consistency properties. Now, how do we do this? Well, a consistency property, as I said, is made up of approximations to a model. You only need to say that the ground set for the poset is the set of conditions, the set of approximations, and a condition is stronger if it has more information for the model. Now, with this forcing definition in mind, let me convince you that the definition for consistency properties is very canonical for this, because all the elements in the definition of consistency properties are talking about dense sets, about generics meeting dense sets. So, consider, for example, the disjunction, which is the most problematic one. So you have your infinitary disjunction in a small s, which belongs to a consistency property. You look at the definition, and it tells you that for one of the elements in the disjunction, you need to be able to continue with this. Okay? Well, but this is precisely the definition of extending a condition in this forcing. Okay? You consider the dense set given by the disjunction and the conditions that realize one of the formulas. Well, then the definition of a consistency property tells you that this set is below the condition, is dense below the condition. Okay? So whenever you take a generic, if the generic contains a disjunction, well, it will meet this dense set. And if it meets the dense set, it will contain one of the realizations. Okay? Now, why is this important? Because of the following result. So this was proved first by my friend Ben de Bont and his advisor Boban Velikovic, and then we got the same thing with Matteo. And it says that if you consider an arbitrary consistency property for the type of logic I'm talking about, well, then any element in the consistency property, any approximation to a model, can be extended to a Tarski model in the generic extension. Okay? Why is this nice? Because again, we have the same corollary as before. If you want to force a model for a sentence, you have to be able to do it like this. Two valid model, yes. So, again, the proof of this corollary below is not very informative itself. But the meaning is that if you want to force something, later on I will discuss a bit what kind of things you might want to force, well, then this should work. Okay? Now it's for us to be good or not good enough to find the right consistency property to it. Now, why do I introduce these theorems now? Well, because they allow to build models. Well, first, let's recall what Mansfield did in the 70s. This is one of my favorite papers. It's only 2 pages. And it proves that if you have a consistency property for these more general infinitary logics, okay, let's not worry about what they are. Well, and you have a consistency property, then the elements are Boolean consistent. Now we come back to these Boolean valued models. And the thing is that you take a consistency property, any element is consistent in a Boolean valued model. Now the problem is that Mansfield models are not mixing in general. And this is one of the reasons for which we need to forget the second kappa on the logic and restrict to L kappa omega. But this is the result that guided us from the beginning, and what we get, the Boolean valid version for mixing models. Okay? So you have a consistency property for L kappa omega, then you take any condition in your forcing notion, well, then it has a Boolean valued model with the mixing property. And this says that if you look, so if you recall the first slide, I was not saying I'm going to talk about forcing. What I said is we are going to discuss the relation between infinitary logics and Boolean valued model. And the point is that I believe that the balance they have together is the same as Tarski model has with first order logic. Okay? Why do I say that? Well, first, we have this conservative compactness, which can be seen as the generalization of compactness. Second, we have completeness, but I don't want to introduce the proof system here. And we now also have interpolation. Okay? So SH here means shifts, so it is intended for mixing models. Okay? So if you have two infinitary sentences and one implies the other, well, you can find an interpolant in the common language which says it is implied by the first sentence and it implies the second sentence. Okay? So this is the most natural translation of interpolation. And then the other theorem I mentioned a while ago was omitting types, and this is my favorite one. And it says that you have omitting types for L kappa omega for Boolean valued models. So you have a theory which is Boolean consistent, and you have a type. If the type is not isolated, and be careful because for infinitary logics, not to isolate a type, this is more difficult than in first order logic. Well, then you can produce a mixing model that realizes the theory and omits the type. Now, if we summarize, we have infinitary logics and Boolean valued models. And we have argued that for this setting, we have compactness, interpolation, omitting types. Well, I didn't mention completeness. And we have a very good tool, which is the model existence theorem for building models. I believe this argues that these two objects are in very good balance, and they are a very good setting to force. Okay? So now let's come to the last item in this talk, which is how to iterate forcing notions. First thing, an iteration here is not a forcing iteration. Might sound weird, but it's a sequence of formulas. Now, this is the slogan one has to keep in mind. And the reason is that for any sentence, there is a canonical consistency property to force with. Okay? So if you have a sequence of formulas, you have a sequence of partial orders. Okay? But again, this is not a forcing iteration in the sense that you have complete subposets and things like that. This is more abstract. And the point is that this consistency property you attach to the formula forces that there is a Tarski model of the sentence, okay? So before I promised that we would eventually come back to Tarski models. Now is the time. So you force and you realize a model, and which is this consistency property? Well, this consistency property is made up of finite sets of subformulas of your sentence that are Boolean consistent with it. If this conservative compactness was a bit clear to you, this should sound very natural. Because recall that for conservative compactness, we said if the weak formula we consider finite sets of subformulas of it, then the strong formula something. Well, this consistency property contains all those elements. And the point is that it forces the model. Well, the fact that it forces the model is, for those that know about this, is almost trivial. The important part is that it will allow us to build nice models of it. The difficult part. How do you iterate? You take a sentence in a language as big as you want, because kappa here can be anything. And the first thing you do is you find a conservative strengthening of it that allows you to do one step. Okay? Should you be able to do this for all successor stages? At limit stages, you arrive to something that is also a conservative strengthening by the conservative compactness theorem. Because if you build one by one, they will be finitely conservative. You take the conjunction, conservative compactness tells you that this is still a conservative strengthening, and you can continue the iteration. And this is the main reason for which conservative compactness is useful for this type of iteration. Well, I didn't say it. Okay. I will give an example now, but the point is that it has to be a conservative strengthening. Okay. Anything apart from that, as you want. So, the nice thing about these forcings is that they are made up of sentences. If they are made up of sentences, we can make formulas talking about the forcings themselves. If you take a dense subset of our forcing, you can write an infinitary sentence saying you meet this dense set. Take a disjunction and you say one of the elements in the dense set is realized. Now, the nice point that this formula is a conservative strengthening. In what sense? In the following, even stronger. So you take any arbitrary family of dense sets for your forcing, then the formula, the original one, together with the sentence saying you meet all these dense sets, this is a conservative strengthening. This is the first example we found, and this is the one that guided us from the beginning. So let's prove it very fast, because the proof is very easy. So recall, what does this conservative strengthening say? You take a set of sub-sentences, and you need to show that they are consistent with the strong formula. So you take those sub-sentences, and you need to show that they are consistent with the strong formula. The first thing is that because T is inside our consistency property by construction, if you force with it, you get that the model realizes this T and the original sentence. This is the model existence theorem. You take an element in a consistency property and you force with it, well, you obtain a model of that. So we have realized the two sentences on the left. It remains to realize the new elements. But how do you do that? Well, you fix little I, you fix one dense set. Well, since it is dense and you have a generic for your consistency property, they have to meet. If they meet, you have one S in the intersection, which means there is another S inside the generic. Again, model existence theorem says anything that is in the generic will be true in the model. You get that the model also realized this little S. And hence, you have realized the whole sentence. Okay? This sentence is somehow just putting all with it together. Okay? This is like the first conservative strengthening one comes up with. And now let me give another one that might be a bit more interesting. I will be very sketchy because I need to finish, but let's say you want to force something in a stationary set preserving way. The problem is that our languages, even if they are very strong, they don't talk about the forcing language. They only talk about the language they know. But let's say you have a name for a club of omega 1. Well, in the first step, you might want to add a predicate to talk about this club subset of omega 1. Because if it is not in the language, let's add it to the language. Now the thing is that one can write an axiom in the expanded language, so in the language expanded with the predicate, to ensure that the original club and the new predicate agree up to some countable ordinal. Okay? Now if you can do that, you can write another axiom that is called AS, because this is originated in the Aspero-Schindler proof, and says that if you have a club name and you have a stationary set, well, you can write an axiom that says they meet. Now, what is very nice, and I leave that for another presentation at some point, is that this is a conservative strengthening of the original formula. when the original formula psi has some property, okay? So how do you finish with this iteration? Well, as they did in their proof, you take a diamond sequence. At each step, you seal one stationary set. You take conjunction at the limit stages because you are able to. And if the diamond tells you that every club and every name for stationary sets appear before, your finite poset is a stationary set preserved and produces a model of the original center, okay? If you recall, I said that we had a goal at the end of the line, and this was that goal. If your formula is nice enough, and I'm not going to formalize that today, you can do all this iteration and get to a stationary set preserving force. Now, why is this nice? Well, first, you can write a formula, an infinitary sentence, and this I'm very sketchy. The ones that know how to prove Mn++ implies stars should understand. But the proof is forcing in a stationary set preserving way the technical part that a Pmax iteration exists, okay? Pmax iteration witnessing that the dense set meets the generic set. When you write a formula describing that Pmax iteration, then you show that it has this nice property, and when you show it has this nice property, you can do an iteration of consistency properties, and the last one will force this formula in a stationary set preserving way. And I think this is my time. Thank you very much.